Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and materials subject. So in this subject already we have covered theory part and then problem solving and then problem solving module, and then we are discussing about question bank. So in this today's session I want to discuss about bending stresses questions. So in examination, so how they will ask and how to attempt the question while giving the related to bending stresses topic. You should know about the course outcome. So analyze the student should be able to analyze the theory of simple bending. So already we have covered theory part and we have derived the equation, bending equation in simple pure bending topic. So in this, they can, after completion of this topic, then student should be able to analyze the theory of simple bending for illustrating the distribution of bending stresses across the section beams under loading. So whenever the beam is subjected to loading, so the bending stresses will be induced in the beam. So how it will distribute the bending stresses, they can illustrate. So this is the main outcome. So now the question number 1. So these questions are taken from a question bank. So in examination, they are related to the bending stresses of the theory part. So they will ask sometimes explain the following. So what they have asked in this question, explain the following bending stresses in beams. So what are the bending stresses in beams? Explain briefly. And what is the position of neutral axis? So and the moment of resistance. So what is this moment of resistance? And the modulus of section. So section modulus of various sections. So first you should explain about the modulus of section and then section modulus of various sections. So these are the topics given as a question number 1. So explain the following. Now one by one we will see what are the bending stresses in beams, what is the position of neutral axis, and what do you mean by the moment of resistance, and what do you mean by section modulus, and then various section modulus formulas also we will see once again in this question bank discussion. So bending stresses in beams. So introduction is the bending moments and shearing forces are set up at all sections of a beam. So already you know we have learned in shear force and bending moment diagrams topic. So all bending moment and shear forces are set up at all sections of the beam when it is loaded with some external loads. So whenever the beam is loaded with some external forces, so they will say some shear force and bending moment will be set up in the beams. As a matter of fact, the bending moment at a section tends to bend or deflect the beam and the internal stresses resist its bending. So whenever the bending moment at a section tends to bend or deflect, the beam and the internal stresses resist its bending. So the process of bending stops when every cross section sets full resistance to the bending moment. So that process, the bending stops when every cross section set up full resistance to the bending moment. So that internal stresses, resistance offered by internal stresses is called bending or bending stress. And the relevant theory is called the theory of simple bending. So now bending stress is the combined effect of both tensile and compressive stresses. So what he has asked in this, the bending stresses in beams. Explain about bending stresses in beams. Clear? So the bending stress stresses means what? So the resistance offered by the internal stresses to the bending is called bending stress. And the relevant theory, that is called pure bending theory or simple theory of simple bending. Already we have derived that bending equation also. So, but this bending stress is the combined effect of the both tensile and compressive stresses. See in this diagram, the bending in beams shown after deformation, before deformation. Before deformation, the beam without load shown here. So after applying movements, the bending moment due to the load, the bending moment will be induced in the beam. So the horizontal axis becomes a curved one, and vertical lines remain straight at a rotate. So after deformation, so these are the horizontal lines. So it becomes a curved one, but vertical lines are remains straight, will not move. So some deformation will occur. So that is phenomena. That phenomena is called as bending. See in this simply supported beam, shown example here, simply supported beam. In simply supported beam, the bending after applying load, suppose the center load is acting at its center, so it bends like this. So this phenomena is known as bending in beams. So already we have discussed in deflection of slope and deflection of beams also. So this bend, how much deflected, that is why, and how much twisted this angle. So what is the slope, theta A and theta B. Suppose this A and B reaction supports. So RA and RB. So these two, the slope and deflection topic is separate. Already we have covered in previous session. So now we are discussing about what are the bending stresses and what do you mean by bending stress, and what is the bending in the beams, the phenomena. So you see in this one end is fixed and supported, another end is roller support. So whenever this the point load, UDL and the movement also applied. So due to this due to this load, see the beam bends like this. So the above, the top portion undergone compression and the bottom one is tension. Yeah. So top layer subjected to compression and bottom layer tension. See in this cantilever beam. The cantilever beam, one end is fixed. One end is fixed, other end is free. Free and fixed. 2 point loads are acting here. Point load, W1 and another point load W2. So after loading, it deform like this. So initially, so this is after deformation. So after deformation, the bottom layer undergone compression, top layer tension. So one is compression, another one is tension. So that's why the bending stress, already here I told you, bending stress is the combined effect of both tensile and compressive stress. So not only single tensile or compressive stress. Clear? The bending in beams and bending stress. So in examination, how to give answer like this. First you should write introduction about the bending stresses in beams, and then the definition of bending stress, and then draw 2-3 diagrams examples you should give with diagram need sketches the bending in beams. You can take any beams, the simply supported beam or cantilever beam or overhanging beam, types of beams already we have studied. Clear? Here you can give any example. And then next second bit is second one, position of neutral axis. What he has asked, explain about the position of neutral axis. What is this neutral axis? The line of intersection of the neutral layer with any transverse cross section of a beam is known as neutral axis, that section. So I will show you in diagram the line of intersection of neutral layer with any transverse cross section of beam. So that means, it does not involve in any bending. So see in this example, so the neutral axis of the beam so this neutral axis of the beam in NA does not involve any type of loading, the compression or tension. So it means there is no change of dimensions. So in neutral axis, there is no change of dimensions. It remains same. Above the top and here see the neutral axis is same. So there is no deviation. But the top layer will be compressed and top and bottom is elongated due to the bending. So the position, how do you calculate the distance of neutral axis from its section, cross section? So we have seen that one side of the neutral axis there are compressive stresses, whereas on the other there are tensile stresses. At the neutral axis there is no stress of any kind. So already I told you, at the neutral axis there is no stress. Whereas on the other there are tensile stresses and sometimes compressive stresses. One side compressive, another side is tensile. So it means that at neutral axis there is no load and no stress. So that is called as neutral axis. Now position. Suppose take this section. The cross section is PQ, the layer, and the neutral axis is NA. So consider a section of beam as shown in the figure. Let neutral axis be the neutral. Let NA be the neutral axis of the section. Consider a small layer PQ of the beam section at a distance y from the neutral axis. At a distance y you take from the neutral axis as shown in figure. So let calculate the small elemental area of the layer PQ. This is a element taken, and delta A is area of the layer. We know that the intensity of stress at the distance y. So from its neutral axis, what is the intensity of the stress at this point PQ layer? So stress is equal to y into E by R. So as per bending stress equation, sigma by y is equal to E by R is equal to M by I. So this is the bending stress equation, bending equation in theory of pure bending, simple bending. We have derived this equation. So from this equation, write this equation, sigma is equal to y into E by R. So take this 2. Since sigma by y is equal to, so now the force on the layer is equal to stress on layer multiplied with area of layer. So it's sigma stress multiplied with area of layer is delta A. So already we have delta A, area of the layer PQ here shown, and already we have calculated stress on layer. So now write down the force on the layer, y multiplied with E by R multiplied with delta A. So but we know that the moment of any area about an axis passing through its centroid is also equal to 0. The moment of area about axis passing through the centroid. Suppose you take this cross section. So CG, the center of gravity, and the neutral axis also passing through the center of gravity. So the moment of any area about the axis passing through the centroid is also 0. Since the neutral axis coincide with the centroid axis. The center of gravity axis, suppose in a triangle section, so neutral axis this one, and the center of gravity is CG. The center of gravity axis is different with the neutral axis, not coincide. So if coincide, in this case, the moment of any area is 0 about any axis passing through the center equal to 0. But in this case, the neutral axis coincides with the centroidal axis. The centroidal axis of a section gives the position of neutral axis. So how much, that is the position, how much distance it is located, the center of gravity axis is located, or neutral axis is located from its center of gravity, how much. So that is y bar. Clear? So this is the answer related to the position of neutral axis. So third one, so bending of stresses beams completed, position of neutral axis also we have discussed. The third one is moment of resistance. So what is this moment of resistance? So the moment of resistance means on one side of the neutral axis there are compressive stress, and on the other there are tensile stress. These stresses from a couple, these stresses, these compressive and tensile stresses form a couple whose moment must be equal to the external moment, that is M. So already we have taken the layer and neutral axis also have discussed, and the position, the neutral axis position from its say layer, bottom layer, that is Y. On one side of the neutral axis there are compressive stress and tensile stress. So combinedly these two stresses form a couple. So that is called as the moment of this couple. The moment must be equal to the external moment. So the moment of this couple which resists the external bending moment is known as bending the moment of resistance. So whatever this formed the couple resist the external bending moment is known as moment of resistance. Here consider section of the beam shown in figure. Let neutral axis be the NA be the neutral axis of the section. Now consider a small layer PQ of the beam section at a distance y from the neutral axis. So y distance from the neutral axis shown in this. So here the moment of resistance already we know the previous we have calculated that the stress intensity of stress at a distance y delta A have taken area of the layer PQ, and also note that the intensity of stress at a distance y sigma is equal to y into E by R. The stress on layer and multiply with area of layer given equation. Now come to the moment of resistance. So the moment of resistance is let M in Newton mm. I is the moment of inertia in mm to the power of 4, and sigma is bending stress in Newton per mm square, and y is the distance of a section from neutral axis in mm. So E is Young's modulus Newton per mm square, and R is radius of curvature. So now write down the equation. So the moment of resistance definition is completed, and then come to the modulus of section. Fourth one. So the stress, the sigma will be maximum when y is maximum. Hence the above equation can be written as, in previous equation, y into E by R into delta A. So from bending equation actually, bending equation, sigma by y is equal to E by R is equal to M by I. So sigma by, here you can write in terms of Z. Z means the I by Y term is called as Z. That is modulus of section. So M is equal to sigma maximum stress will be obtained when Y is maximum. So that's why I by Y maximum. So you can say that Z is equal to I by Y. So I is moment of inertia. Y is the distance of section from its neutral axis. So that you can write the final equation, M is equal to sigma max into Z, or sigma max or M by Z, or Z is equal to modulus of section, Z is equal to M by sigma. If you know the bending stress and the bending moment, you can calculate modulus of section. And if you know the moment and section modulus, we can calculate sigma max, the maximum stress. So the stress will be maximum whenever the Y is maximum. So the section modulus of various sections. So we will see in this rectangular section. Suppose the rectangular cross section. So B and D. So we know that the moment of inertia of the rectangular section about an axis through its center of gravity. So I is equal to BDQ by 12. So we know that the moment of inertia of a rectangular section about an axis through the center of gravity I is equal to BDQ by 12. What is B? The B is width and D is the depth of the section. So modulus of section already we have seen in previous slide, Z is equal to I by Y. So now substitute in place of I BDQ by 12 and then Y is D by 2. So the neutral layer, neutral axis distance is D by 2. Not passing through the axis of the center of gravity. See, passing through the center of gravity, so there is no area, moment area. So now calculate Z value. So we will get BD square by 6 for rectangular section. So similarly, take another section, hollow rectangular section. The width B and the depth D and D by 2 and width is small b inner. So the previous rectangular section there is no hollow, only one width and depth. But having the hollow rectangular section inside dimensions also there. So width and small d. For this, how do you calculate the moment of inertia? See the BD by 12 minus capital BD by 12 minus small bd by 12. The Y maximum is D by 2. So now you can calculate Z. How do you calculate Z? I by Y. So Z already written in the previous slide, I by Y. You know that formula. So what is I? I is capital DQ by 12 minus small d BDQ by 12 divided by Y is capital D by 2. So now you can write, so take common 1 by 12 capital BDQ minus small bdq into 2 by d. So you can write the final equation, Z is equal to 1 by 6d bdq minus small bd for the hollow section. For the rectangular section, bd square by 6. So next, hollow circular section. The circular section already you know, internal having internal diameter and external diameter. The d is external dia and small d is internal dia. So here calculate the I value. I is 5 by 64 multiply with the capital D to the power of 4 minus small d to the power of 4. So actually for solid one, suppose only solid circular shaft, so having only d diameter. For this the moment of inertia pi d to the power of 4 by 64. But hollow circular section, use this formula pi by 64 inside bracket capital D to the power of 4 minus small d to the power. So the Y maximum is capital D by 2. So the Z is, now calculate Z value, I by Y. I is 5 by 64, capital D to the power of 4 minus small d to the power of 4 divided by y is capital D by 2. Now the 64 d to the power of 4 minus small d to the power of 4 into 2 by d. So here 32. So z is equal to pi by 32 into d to the power of 4 minus small d to the power of 4 multiply with this d. So obtained the equation z is equal to pi by 32 capital D to d to the power of 4 minus small d to the power. So these are the section modulus of various cross sections. See, in this bending stresses, already we have covered, we have done a lot of problems on this pure simple bending, and also covered theory part derivations. But in this question bank, have selected this theory part. So why? Because this the position of neutral axis or bending stress and beams and moment resistance and section model, these are the basics for bending stresses. You know the bending equation and you can apply, you can solve the problems by using bending equation. But how to give answer exactly the point to point in examination for the following words, you should know. So that's why here selected topics are bending stress and beams, and we have discussed about bending stresses and beams, and also position of neutral axis, and also moment of resistance, and then modulus subsection, that is Z, we have learned, and section modulus, various sections, section modulus, how do you calculate? So apply this I by y formula section modulus. So that up to now, so far we have discussed about the bending stresses and beams, we have studied, and then position of neutral axis, what is this neutral axis, and how to locate the position of neutral axis for various beams, and then moment of resistance. So the moment of this couple which resists the external bending moment is known as moment of resistance, and also calculated. And then section modulus or modulus of section, both are same. So how do you calculate? By using bending equation. The bending stress equation is very important for bending problems. Here use this equation. The derivation parts also we have completed in earlier sessions. And rectangular section, the section modulus. So for moment of inertia is b dq by 12. I, you know, b dq by 12. And then the I by y. So y is d by 2. Substitute these two values, you will get z value. So that is bd square by 6. Next, hollow rectangular section. So high bd by 12 minus internal dimensions also there, the b into small d. Subtract those inside dimensions, you will get moment of inertia of the hollow rectangular section. So substitute this I and y, you will get z. Similarly, a hollow circular section, I is equal to pi by 64 d to the power 4 capital D to the power 4 minus small d to the power 4. So y max is d by 2. So the z is 5 by 32d into the small d to the power 4 minus capital D to the power 4 minus small d to the power 4. So like this, need to give answer for the bending stresses topic. So these are the references I have taken. So S. Ramamurthy. The title of the book is Strength of Materials. And R.K. Rajput. Title of the book is Strength of Material. Publishers are H. Chand and Co. and R.K. Bansal, Textbook of Strength of Materials, Lakshmi Publications, and R.S. Kurmi and Gupta. Title of the book is Strength of Materials. So you can take latest version and take any one reference for further more clarification. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.